Welcome back, everybody. This is our second session or second class in JEE mains previous year questions for chapter Ray Optics and Optical Instruments of class 12th. Before this video, we have made one video in this series, and that video is available on our channel's playlist section. We have also started similar series for NEET previous year. So if some of your friends are preparing for NEET, then they can also watch those videos. And if you find these videos helpful, useful, then do press the like button, share them, and subscribe to our channel. It helps a lot. And if you find these videos helpful, then do press the like button, share it, subscribe to our channel. And also, if you like to support us, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Now, with this, let's start today's video. In the previous one, we covered up to question number 8 or something. Yes, this was the previous video in which we covered up to question number 9. Now let's start with the next one. So here, to get 3 images of a single object, one should have 2 plane mirrors at an angle of. So here it is mentioned that we need 3 images. So means number of images here is odd. And for odd case, we know that n is equal to 360 by theta minus 1. So here we will get 3 is equal to 360 by theta minus 1. So 4 will be 360 by theta, and from this theta will be 360 by 4, that is 90 degree. So that is option B here. Let us move ahead. If two plane mirrors are kept at 60 degree to each other, then the number of images formed by them is. So to find number of images, we can write that n will be 360 by theta, and here that will be equal to 360 by 60, that will give us 6. And as the number of images are always odd, so what we have to do, we have to subtract 1 here. So that n will be 6 minus 1, that will be 5. So finally we will get 5 images. So option A is right for this one. In the next one, an observer can see through a small hole of a side of a jar, radius 15 centimeter, at a point at a height of 15 centimeter from the bottom. The hole is a height of 45 centimeter. When the jar is filled with a liquid up to height of 30 centimeter, the same observer can see the edge of the bottom of the jar. If the refractive index is n by 100, where n is integer, find the value of n. So here, in the initial case, when this jar is empty, then he can see, means light travel in a straight path, and he can see up to this point. Now we know that base is 15 centimeter, so this height will be equal to 30 centimeter, and the radius here, yes, here it is. Radius is 15 centimeter, so this will be the diameter. So this will be equal to 30 centimeter. So here we can see that both of the sides are equal. So if sides are equal, means what will happen, that this angle will be 45 degree. And if this is 45, then from the parallel rays, we can find out that angle of incidence is 45 degree here. Now, coming to the that when jar is filled, so suppose when jar is filled, so our jar will look like this. That suppose this is our jar, and now it is filled up to 30 centimeter. So suppose this is now filled up to 30 centimeter. So this is 30 centimeter, and as per mentioned, that bottom is visible. So our incident light will be like this. Let me adjust the thickness first. So this will be the incident light, and after refraction it will be going like this. Here if we draw the normal, so normal will look like this. Now we know that this angle is 45 here, and this angle will also be going to be 45. because this is 45 and this will be 90 minus 45, so this is going to be 45. Now this height is 30 centimeter and this one is 15 centimeter and this is also going to be 45. So let us mark some points here. Suppose this is point O, this is A, this is B, this is C, and this is D. Now let us first take the triangle, this one, ODC. So this is our first triangle, ODC. Now we know that this side is 15 centimeter and this angle is 45. So this angle is also going to be 45 and this side will become 15 centimeter. So if this distance is 15 centimeter, then this OB distance will also going to be 15 centimeter because diameter is what we have, diameter is equal to radius is 15, so diameter is 30 centimeter. Now if we draw it down here, this is 30 centimeter and here we have angle, suppose beta. Now we know the two sides, so tangent of beta will be equal to perpendicular by base, that will be 13 by 15, 30 by 15. So here we will get tangent of beta is equal to 2. Now from this we can draw a triangle that if tangent of beta is 2, this angle is beta, so this is equal to 2, this is equal to 1. So from the Pythagoras theorem this will be root 5, and from this we can write that sine of beta will be equal to 2 by root 5. Now at this point we having at this point refraction is there, so we can apply Snell's law that refractive index of the air into sine of incidence, that is 45, should equal to refractive index of the glass into sine of beta. So refractive index of air is 1 and sine of 45 is 1 by root 2 into refractive index of glass into 2 by root 5, and further from this we will get mu of g is equal to root 5 by 2 root 2, and this will on solving will give us 1.581. Let me rewrite it, 1.581, and that can be written as 158 by 100, as we have to find answer in the form of n by 100, so n will be equal to 158 here. So with this, let's start the next one. A light ray enters a solid glass sphere of refractive index mu is equal to root 3 at an angle of incidence 60 degree. The ray is both reflected and refracted at a further surface of the sphere. The angle in degree between the reflected and refracted ray we have to find out. So let us first draw a sphere here. So assume this is our sphere, and let me change its color slightly because for better visibility, let's go with this one, and thickness. So suppose this is our sphere and now there is an incident light on it. So suppose this is incident light, and what will happen, it will get refracted. So after refraction is like this, and there will be another refraction there. So from the second refraction it will go like this. Now there will be reflected light on the both sides. So suppose this is the first reflected light here. Oh sorry, first reflected light will be like this, and suppose this is the second reflected light. Now what we can do, we can draw normals. This will be the first normal here and this will be the second normal here. Now as per statement that our first angle of incidence is 60 degree, so this angle is 60 degree here, and here refractive index is root 3. So what we can find out, we can find this angle. So suppose this angle is I here. So using Snell's law, we will get refractive index of air into sine of 60 into root 3 into sine of I. From this, our I will be 30 degree. Now, we know that normal passes through the origin of the sphere. So this line will further pass like this, and this line will go like this. And now, if suppose this is O, this is A, and this is B, then OA is equal to OB is equal to radius. So this triangle, in this triangle we have two sides equal. So if this angle is I, then this angle will also be I, and I is 30 degree. So this angle will be 30 degree. And from the reflection law, that angle of incidence is equal to angle of reflection. So this angle is also 30 degree here. Now at point B, we can again apply Snell's law. So root 3 into sine of 30 will be equal to 1 into sine of, suppose this angle is theta, sine of theta. And when we solve this, as due to reciprocity, because these are just reciprocal of each other, both equations, so theta will be 60 degree. So this angle is 60 degree. Now we have to find out the angle between the reflected and refracted ray on this surface, and that has to be found on the further surface, means not on the this one, we have to find on the this surface, and that will be equal to this value. Suppose that is x, so we will have 30 plus x plus 60 should be equal to straight line or 180 degree, and from that x comes out to be 90 degree. So answer to this question is 90 degree. Let us move ahead. A vessel of depth 2h is half filled with a liquid of refractive index 2 root 2 and upper half with another liquid of refractive index root 2. The liquids are immiscible. The apparent depth of the inner surface of the bottom of the vessel will be. So we are going to take assumptions here that we are dealing with small angles, because only in case of small angles what we can write, that d apparent is equal to d actual by refractive index mu. As here we have two liquids, so it will be d1 by mu1 plus d2 by mu2. Now height of each liquid is h, because it is half filled with one liquid and half filled with another liquid. So it will be h by 2 root 2 plus h by root 2. And on solving, what we can do, we can take LCM. So 2 root 2 as LCM, this will be h, and this will give us 2h. So this will be 3h by 2 root 2. And here I think we have 3h by, it is written in 4. Okay, what we can do, we can multiply it by root 2 and multiply root 2. So this will be 3 root 2h by 4, and that is option D. So option D will be the right one here. Let us move next one. There is a small source of light at some depth below the surface of water, refractive index 4 by 3 in a tank of large cross-section area. Neglecting any reflection from the bottom and absorption by the water, percentage of light that emerges out of the surface is nearly. Use the fact that surface area of the spherical cap of height h and radius of curvature r is 2 pi r h. Now this question is basically related to total internal reflection. So let me show what will happen. So suppose this is a water tank. Suppose let us take a water tank here. Suppose this is our water tank and it is filled up to some height. It is filled with up to some height, and this is a 3D water tank, and here we have placed a source. So what will happen, that when light will travel from the source, suppose this is the light traveling from the source, at certain angle this light will suffer total internal reflection, so it will move along the surface of the water. So if we want that if we want to calculate that out of what is the area out of which light is coming out, then this will be the area in this conical shape here, like this will be the spherical area out of which light will be coming out, and outside of this sphere or this circle, this as it is in 3D. So outside of this circle, light will be getting totally internally deflected. And so what we can do here, first we will calculate this angle theta. That if we calculate here, if this is the angle of incident theta c, that up to which light will, after which light will be getting totally internal reflected, so this will also be theta c. So we know that sine of theta c or theta c is equal to sine of theta c is equal to 1 by mu, and refractive index is 4 by 3 here, so sine of theta c will be equal to 3 by 4. Now as we can see, and I have already told, that it is forming an cone, and for a cone, the remaining part here, so suppose this is a cone. Now we know that this cone is a part of a bigger sphere, out of which light, out of this remaining part, light cannot come out, but light can only comes out through this area. And if we know this angle theta, then using solid angles, we can convert it. Solid angle of the cone here, suppose that is phi, will be equal to 2 pi into 1 minus cos of theta. And if we know that sine theta c is 3 by 4, then cos of theta c, from making a triangle, that this is 3, this is 4. So this will be equal to 16 minus 9, that will be root 7. So cos of theta here will be 1 minus root 7 by 4. Now total solid angle is 4 pi, and out of 4 pi we are getting light only through this part of the angle, so percent. And out of this angle, this is the solid angle, and we know that total solid angle is 4 pi. Now out of 4 pi we are getting light through this, only through this angle, so the percentage of light received will be 2 pi into 1 minus root 7 by 4 divided by 4 pi into 100, and this will give us 17%. So answer will be option C. Let us move to the next one. So here, the critical angle of a medium of specific wavelength, if medium has a relative permittivity 3 and relative permeability of 4 by 3. So to find the critical angle, what we need refractive index. So, and for refractive index, how can we calculate refractive index? That will be find out using velocity by speed of light. That is that's how we can get refractive index. So velocity inside a medium of a EM wave is equal to mu r into mu node into epsilon r into epsilon node. Now this can be written is like mu r into epsilon r into mu node into epsilon node. Now this term is equal to C. So basically V will be equal to mu r, and epsilon r is given to us. So 3 into 4 by 3 into C here. And from this V by C, that is basically the refractive index. Oh, sorry. C by V, that will be the refractive index, that will be equal to root 4. And from this mu or refractive index is equal to 2. Now critical angle will be, we know that theta of C is equal to sine inverse 1 by mu. So sine inverse 1 by mu, that will be sine inverse of 1 by 2, and that is going to give us 60 degree, oh sorry, 30 degree. Let us move to the next one. So here concave mirror has a radius of curvature 40 centimeter. It is at the bottom of the glass, has a water filled up to 5 centimeter. See figure, if the small particle is floating on the surface of water Its image as seen from the directly above the glass is at a distance d from the water surface. The value of d is close to. So this mirror is going to this concave mirror will form the image of this particle. So first we have to use mirror formula. So that will be 1 by v plus 1 by u is equal to 1 by f. Now radius of curvature of the mirror is 40 centimeter. So focal length will be 20 and it will be negative as it is concave. So we can write that 1 by v is equal to 1 by f, that will be 1 by minus 20, and minus 1 by u, and that is negative of 5. So when solve this, we will get v is equal to 20 by 3 centimeter. So it is positive, means image is formed at some point here. Image will be formed at some point here. Now total distance from the observer, assuming that observer is at the same point as the particle. So total distance will be 5 plus 20 by 3, and this will be equal to 35 by 3 centimeter. Now this is the actual distance, and as we can see that we are looking through water. So what we will see, we will observe the apparent distance. So here d apparent will be equal to 35 by 3, that is the original distance by the refractive index of the water, that is 1.33, and from this we will get 8.75 centimeter, that is closest to the option C here. Now let's move ahead. A transparent cube of side D made of material of refractive index mu2 is immersed in a liquid of refractive index mu1, where mu1 is less than mu2. The ray incident on the face AB at an angle theta shown in the figure. Total internal reflection takes place at point E on the face BC. The theta must satisfy. So we have to find out condition for theta. So for that, assume that if this is theta, suppose this is gamma and this is phi. Now at this point what we can write, we can write Snell's law, that mu1 into sine of theta is equal to mu2 into sine of gamma, and gamma will be from here with that gamma plus phi is equal to 90, or from that gamma will be 90 minus phi, and from this we will form an relation that mu1 sine of theta is equal to mu2 into cos of phi. Now from this, sine of theta is equal to mu2 by mu1 into cos of phi. Now let's come to this point where total internal reflection is happening. So for this point, we can write that sine of phi must be equal to 1 by mu2. And from this, if this is value of sine of phi, then we can write, we can make a triangle that this is phi here. So this is 1 and this is mu2. So this side will be mu2 square minus 1, and from this cos of phi will be equal to under root mu2 square minus 1 by mu2, or that will be equal to 1 minus 1 by mu2 square. Oh, sorry, we need to do a correction here, that outside material is not air. In the outside we have refractive index mu1, so this will be mu2 by mu1. This will be mu1 by mu2. Relative refractive index will be mu2 by mu1, and sine of phi will be mu1 by mu2, inverse of that. So here this will be mu1 by mu2, and this will be equal to mu1 square minus mu2 square. Okay, let me correct this one, because this whole scenario needs to be changed. Okay. Now let me redraw the triangle again. That if this is phi, and so this will be mu2 and this will be mu1, and this will be equal to mu2 square minus mu1 square. So now cos of phi will be equal to under root mu2 square minus mu1 square by mu2, and this can be written as under root 1 minus mu1 square minus mu2 square. Now we can substitute this value here. So sine of theta will be equal to mu2 by mu1 under root 1 minus mu1 square by mu2 square. Now this can be further written as like that sine of theta is equal to mu2 square minus mu1 square minus 1, mu2 square by mu1 square minus 1. Take mu2 and mu1 inside the square bracket, and from this theta is sine inverse mu2 square by mu1 square minus of 1. Now while driving this condition, what we assume that total internal reflection is happening and light is moving like this. Light is moving along the line EC. Now the value of theta to so for this given condition we can increase value of phi, because if value of phi is less than some critical value, TR naught will happen, and if value of phi is greater than the critical condition, and that is that critical condition, then TIR will happen. So here phi can be increased further. Now if phi is can be increased further means gamma will decrease, because gamma and phi has a relation that both they add to up to 90 degree. So if we can increase phi, then gamma will decrease, and from this relation if gamma decreases, both mu1 and mu2 are constant, then what will happen here, that sine of theta has to increase. Sorry, sine of theta also has to decrease, means the value what we have solved here for the theta is going to the maximum value. Theta cannot go beyond this value, so here theta must be less than sine inverse mu2 square by mu1 square minus 1, and that is satisfied in option C here. Now let's move to the next one. So a ray of light AO in vacuum is incident on the glass slab at an angle 60 degree and refracted at an angle 30 degree along OB as shown in the figure. The optical path length of the light ray from A to B is. So optical path length or OPL is mu into actual path length. So basically it will be uh, mu of air or vacuum. Here we have vacuum into path length in vacuum, that is AO, plus mu of glass into path length of glass, that is OB. Now if this is A, suppose this point is here, we have B, so suppose this is C. So we can write that AO sine 60, sorry, not sine 60, this is 60, so this is 30. AO sine 30 is equal to small a. So value of AO will be twice of A. Now similarly, for this lower triangle, what we can write that OB, and this length is B. So OB cos 30 is equal to B. Now, so from this, OB will be equal to twice of B by root 3. Now refractive index of vacuum is 1. So 1 into 2A plus refractive index of the glass, here it is not mentioned. So let us take or let us calculate using Snell's law here. Let us apply Snell's law at this point, that 1 into sine 60 is equal to refractive index of the glass into sine of 30. So this will be half, so root 3 by 2 into mu g into half. So mu g is root 3 here. So here we will get root 3 into 2b by root 3. Root 3 get cancelled and we will get total optical length is twice of a plus b. That is option D. So with this we end this video here. Hopefully whatever we have covered here is helpful and understandable to you. Again, if you have any doubts or suggestion, you can put them in comment section. I will like to resolve them. And if you find this video useful, then do press the like button, share it, and subscribe to our channel. Also, if you like to donate something, you can scan these QR codes. We will meet in next video.